Dale, who's going to be here with you, right? So may as well do something fun next week, you know, and come find some, right? So play cookies next week, or bowling. Yes. All right, today we have a really hot topic for you. It's been hot for a long time, and I think it's going to be a hot topic for millions of years to come, and that's the subject of radioactive waste and how to clean it up. And we have our own John Tixier here from our School of Engineering, who is going to be telling you all about it. So let's give him a big
Thank you very much, Dr. DeBoer. Yes, School of Engineering. It turns out that there's a engineering meeting today. So when I asked a few I don't know, a month ago or so, when I saw that there was a conflict, I sent a message to Dr. DeBoer and I said, hey, I see that next week is open. Maybe I should trade. He said, well, I don't think anybody will be there. So I didn't realize what day it was. So some of you, how many of you were here last fall when I spoke at the beginning of the year? So there will be a little bit of overlap, not a whole lot, but just by way of introduction, what I talked about was where I'm from, the Hanford site in Richland, Washington, and where the high school is the Bombers. It's their the mushroom cloud in there, a tribute to the legacy of the Hanford site. So this is an aerial view of part of the Hanford site, looking due west towards some of our icons in the Pacific Northwest. You've got Mount Rainier on the right, and Mount Adams on the left, and some of you may be wondering where Mount St. Helens is. Well, if you could see it, 40 years ago, if you could see it, it would be right sort of off the shoulder of Mount Adams. But it blew its top, it blew 5,000 feet off of the top of it. Mount Rainier is about 14,500 feet. Mount Adams is about 12,800 feet. Mount St. Helens was 13,000 feet, and now it's about 8,000 feet. So you can't see it from there. This is a beautiful, clear day in the Pacific Northwest. You can see it. We're on the arid side of Washington, where the mountains are. It's where all the trees and the green. So when you think of Washington, you think of green and wet. That's on the west side. On the east side, it's arid, which is why, one of the reasons why the Hanford site was selected here. But we're going to talk a little bit about what goes on with nuclear waste. Last time I told you about what is radioactivity. We talked a lot about various aspects of radioactivity, radiochemistry, isotopes, decay, half-lives, things like that. So I'm going to take for granted that some of you remember that. It's not going to come into play. It won't be on the test after this. But it has to do with what's going on here at Hanford. This is the biggest, most complex waste site in the country. Hazardous and especially nuclear waste. And so we're going to talk about what it's going to take to clean this up and what's been going on to clean up this site and why we have to clean it up. Okay, some of the engineering and scientific things that are going on. But first, I want to give you some background. We're going to talk a little bit about the history of Hanford, how it got to be where it is, and I'm going to let, I've got a couple of videos here to show you how that works, all right? So bear with me. The podium is not nearly as sophisticated as I thought. So I set up when I was planning my presentation, I was going to do a bunch of multimedia stuff, and the podium can't handle it, so I have to sort of manually do this. All right, so what I'm going to do is show you a couple of videos and comment on them a little bit as we go along. So let's see if we can make this work. Get the display up here. We're going to see about a 5-minute video on Hanford, but I'm going to speed it up just a little bit. And I guess we should turn up the audio here so we can hear.
You giving out samples today?
I didn't bring any samples. All right, so lethal.
While small amounts of plutonium have been produced at facilities in Chicago, nothing of this magnitude or complexity had ever been attempted. Producing plutonium was complex and messy, with the added potential of being catastrophically lethal. The process started with uranium billets that were fabricated into nuclear fuel rods in the 300 area and transported via rail to the 100 area, where they were inserted into one of multiple process tubes in the 30-foot high reactor core. With water from the Columbia River rushing into the reactor, a nuclear chain reaction transformed uranium into plutonium.
It's hard for people to imagine the enormous energy that's produced in a reactor, but as I remember, the flow at that time was like 186,000 gallons a minute. And that water is entering the front face in cold, ice cold, and it's exiting the rear face at nearly boiling temperatures in that short distance of time. And there's 2,004 process tubes that's going through there, so it's hard to imagine the energy that is contained unless you hear.
So every time I mouse over this, it's going to act funny because I can't control it otherwise. But talking about the energy, this nuclear reaction is producing a tremendous amount of energy. When they pull water out of the river at pretty cold conditions, I don't know if he thought it was ice cold. I don't think it was ice cold coming out of the river. But 50 degrees, it was pretty cold water. Running over that, it makes it boil. So there's an awful lot of energy being produced by this reactor. We'll show you some more of the reactor as we go along, but this is what the nuclear reactor looked like back then.
It's just massive amount of energy that you experience. But a startup like that is phenomenal.
After a short cooling off period, the now highly irradiated fuel rods were transported to T-Plant in Hanford's 200 area. T-Plant was one of several enormous facilities, the size of ocean liners. In fact, they were frequently referred to as Queen Marys by Hanford workers. It was here they separated plutonium from irradiated fuel rods, using a complex and massive liquid chemical bath process. T-Plant was the first facility of its kind in the world. Like the world's most elaborate and intricate gold panning operation, the process yielded minute amounts of plutonium, by weight, the most expensive material on the planet. The extracted plutonium was processed into buttons that would serve as the core of the atomic bomb.
So a tremendous amount of uranium was used to create a little bit of plutonium. And what else was made was a whole lot of byproducts. And that's where all the waste comes into play, okay? And the chemistry that's involved in trying to separate the plutonium out of the uranium. And we'll talk a little bit more about that in a minute. But that's what he's talking about now, is how they're getting the plutonium out of the uranium and what you have to do with the leftovers. Well, you put it in a bunch of tanks, okay? Sometimes in the beginning, they just dumped it. So it's part of the cleanup, because back in the 40s, when nobody's ever done this before, you don't really have a good plan, and you're trying to win the war. So we're in the middle of World War II, and the fate of the world is in the balance, right? So we're not too worried about damaging the environment. We're trying to win the war. So that was the focus at the time. And it's hard to grasp that at this point. It's hard to grasp what was going on, the concern that people had about World War II. And now we're concerned about the amount of waste that's there. But we have to maintain that perspective. The priority back then was the security and liberty of our people, okay?
Millions of gallons of highly radioactive liquid waste, a byproduct of this chemical separation process, were stored in roughly 60 underground tanks, ranging from 500,000 to 1 million gallons in capacity. Ultimately, the Manhattan Project was a success, and the long-kept secret was out. The plutonium produced at Hanford was used in the Fat Man bomb, dropped on Nagasaki on August 9, 1945, forcing Japan's surrender and bringing an end to the war. Ushering in the atomic age, Hanford continued to support America's peace-through-strength policies throughout the Cold War, producing enough plutonium to maintain a continual and formidable deterrent for any potentially hostile nation, namely the Soviet Union. However, during these critical wartime and national security missions, the thought of what to do with the resulting waste and what its impact on the environment might be was secondary to the need for immediate production and use of the vital plutonium. Nearly 200 million gallons of this waste was held in underground storage tanks, or worse, returned directly to the ground.
There were two big headers on each side of the reactor, and the effluent was then distributed out to a cooling basin.
25 million cubic feet of buried or stored solid waste. 2,300 tons of spent nuclear fuel. 20 tons of plutonium-bearing materials, and 53 million gallons of waste in 177 underground storage tanks. This waste is the legacy of more than 5 decades of plutonium production, making it easy to see how Hanford became the largest, most complex environmental cleanup effort in the world.
Material.
So you can sort of see how the problem got to be so big with all that waste. So the video in the end was telling you how big the problem is. There's 149 tanks that were built, and since then we built a number more to store all the waste. Those were million-gallon waste tanks. All right. So this is again the issue was not what are we going to do with the waste. The issue was making a place for the waste and trying to win the war. Okay. So here's the Hanford site. It's 586 square miles in eastern Washington. That's half the size of Rhode Island. Okay, it's a big area that the government commandeered from the few people who were living there. About 1,000 people lived there in the first half of the 20th century. And the government identified this as a primo spot because it had power. Grand Coulee Dam had been built in the 30s, not too far away, so lots of power. Largest river west of Mississippi is here, and so lots of water. Maybe if you consider the Missouri River part of the Mississippi River system. And pretty remote, okay? So it was a very ideal place. Up to, in the middle of in the heyday of 1944, 55,000 people came to work there. Just signed up, heard there was work, and came from all over the country to work at Hanford to build. They didn't even know what they were working on. They just had a job. Whatever your trade was, whatever your job was, you did your job. You didn't know what it was for. Nobody knew what they were doing, what it was for. Okay, they knew what they were doing in their little job, their little purpose. But they didn't know the big picture. Couldn't tell anybody what we were doing. Yeah, we're trying to build a bomb to win the war. That was not the point. You know, it's not like the media we have today, where everything gets out left and right. Leaks are all over the place. Leaking was not approved then. So the ongoing process, as they said in the video, once we built the bombs, how many bombs were set off during World War II?
2. 3, 1 testing.
I heard 2, dropped on Japan. How many bombs total went off? 3. The other one was Trinity. The one that was set off in New Mexico as a test, right before that, just to see if we could do it. But we had 2 different kinds of bombs. One was built at Oak Ridge, Tennessee. They were doing the same thing, only different. At Hanford, we're trying to get plutonium and using plutonium to build a nuclear bomb. At Oak Ridge, they were just using uranium. They're building a uranium bomb, enriching the uranium. So we had 2 different bombs to try to make sure at least one of them would work, right? We were able to test one of them. And that's all we had. But after we dropped the second one on Japan, they figured, well, it's going to happen once. Once it happened again, that's when they surrendered. We didn't have another one. That's all I had. So we were able to save a lot of lives by finishing the war. So here's how bad it is, all right? So I said there's 149 single shell tanks. Those 1 million gallon tanks, 75 feet in diameter, 30 to 40 to 50 feet deep, storing this liquid waste. Well, over the years, those tanks, again, we're not focused on long-term storage. We're just focused on the immediate situations. They weren't really designed to last for very long, 15, 20 years, maybe. So what happens again after it exceeds their design life? They still got this waste in it. What happens?
Just start leaking.
They start leaking, yeah. So, so one of the advantages here in eastern Washington is that it's an arid site. There's not a high groundwater table. And so it does leak into the ground, but it's not very mobile. Okay, it's not getting to the river very fast. Still getting there slowly. So there's some concern. So they built how many more? If there's 149 built originally, now we have 177. That's simple math, right? So 28 more tanks were built, but these were double shell tanks. These were meant to be long-term storage. And so they were able to pump a lot of that waste into there. Okay. Oh, you know what? Last time when I was here, we talked about the fact that I couldn't really tell you how to make a nuclear weapon for two reasons. One, because it'd take too long, and two, that's good. So, but I got good news today. Well, maybe good news and bad news, because today we got time. Okay, so how do you make plutonium? No, this is all free and clear stuff. Okay, nobody needs to think that they're going to have to sacrifice their life for the knowledge that's coming out right now. All right. How do you make plutonium? Well, you take some uranium. Uranium-238, which is the common amount of uranium that you find when you get uranium, and you bombard it with neutrons. When you bombard it with neutrons, some of the neutrons then impact the uranium and creates uranium-239. Uranium-239 has a half-life of 23.5 minutes, so it doesn't last very long. It lets off a beta, and it becomes neptunium. And neptunium has a half-life of about 2 days, a little over 2 days, and it decays to plutonium. That's what we're looking for, plutonium-239. Plutonium has a half-life of 2,24,000 years, so once it becomes plutonium, it's not going away very quickly. And that's what we're looking for. We're looking for plutonium. So it takes a lot of uranium, takes a lot of neutrons, takes a lot of to make a little bit of plutonium. Because you're only successful a very small amount of the time. And so what they have is these fuel rods. Okay, these are uranium. These are tooled and shaped uranium rods, and that's what's inserted into the reactor. And that's what's bombarded with neutrons. That's what creates a lot of energy. You've got to keep it cool with the river water. Okay, so the river water is not being contaminated. We're not putting contaminated radioactive water back in the river. It's just used to cool the plant. Okay, so these are talked about the B reactor. Here's the inside of the B reactor. You saw that in the video. So all of those rods go into these slots in here. Okay, this is the B reactor facility. They built. We'll see a slide that has all the reactors on there. So over the course of the World War II, they ended up building 3 reactors. Okay, the B reactor was the main one where we got the plutonium that we used for the bombs. N reactor was the last one that was built, January 1960, and it was actually a production reactor, energy production, dual purpose reactor. And so they were still making weapons grade material out of it, but it was also generating power. All the other ones were just weapons reactors. They've all been decommissioned at this point. They've all been demolished and stabilized, except for B reactor. It's a National Historical Site. So this is what it looks like now. You can still go out on tours. You can sign up for a tour. The National Park Service runs that with local people involved. There's still people working here that were little kids at the time, who were, some of them actually lived at Hanford and were displaced. And told by the government, you got about a month, 30 days to take everything you want and get out, because we're taking your home and your land, and we're not telling you why. But just remember, we're fighting a war, okay? So that has part to do with it. So this is the B reactor, and so here's the chemistry, okay? And it's not a very, I'm not going to go into great details on the chemistry, because one, I'm not a chemist, I'm a mechanical engineer, so I don't really like chemistry. But so when you're working with this stuff, you work with people who like it, know about it, know how to do it. So anyway, the plutonium extraction from uranium uses some pretty bad stuff to work with that. That's to try to pull out the plutonium. Okay, and so as I said, it creates an awful lot of waste, and both in the uranium that's left over and in the byproducts that come out. And in fact, there's a lot of, it's not just the chemical waste. There's, when you're trying to bombard the uranium to make the plutonium, there's a lot of other byproducts that come out. A lot of other decay products are part of this. And so it's a very complex mixture of chemical and hazardous nuclear waste. Cesium and strontium are the main byproducts of this process. Cameron?
Is uranium hazardous as is?
It's radioactive, and so enough of handling uranium you will be exposed to radioactivity. But I've got some. I showed you guys last time. I've got a little piece of uranium in my office. It's not dangerous levels. But the concentration, you don't want to be handling these without some handling, with some tools to handle them.
Isn't that alpha radiation?
Plutonium, the main problem with plutonium is alpha, yeah. And so you can hold plutonium in your hands, but usually you do it in a glove box because you don't want to breathe that stuff in. Anything that comes off of it, you do not want to get plutonium. It's not even going to penetrate your skin, plutonium will. I mean, the alpha radiation won't penetrate your skin. But if you ingest it, it's very bad in your body. So yes, plutonium is generally mainly an alpha emitter. So keeping it safe and keeping the contamination from getting places was very important. So here's the slide that I talked about that has, here's the B plant that was built in 1944, right? And so a couple more were built during the war, D&F to produce more. We didn't end up needing them in a timely fashion, but we kept producing this stuff because now the war ends, World War II ends. This is all recent history. This is all in the last 100 years. World War II ends, and now the Soviet Union is our enemy. They were they were on our side fighting the Nazis during World War II, and now they're on the other side, and they are developing these weapons too. And so they are building bombs and testing them. And so now there's a threat that we would have a nuclear war, that these bombs would keep going off, that we would fight each other with nuclear weapons. And so the impacts or the results of what happened to Hiroshima and Nagasaki would be a routine thing in war, and that would be I mean, war is bad enough, right? People fighting and killing each other, dropping bombs, destroying facilities. But to be using nuclear weapons as a matter of course. And so when you hear about that today, you hear about the threat that North Korea has, that they have nuclear bombs, that they would be willing to another country. Now we say that we're not going to do that. We're not going to go willy-nilly dropping nuclear weapons on something. But that was always the threats with the Soviet Union. So we built more and more and more and more and more. Through the 80s, through the 1980s. And we won. The Soviet Union couldn't keep up. They couldn't stand it. And they collapsed. Through a lot of things, not just the physical and economical pressure, but the social pressure and things like that, where communism fell in 1989. And so we won the Cold War. I got off track with the slide a little bit. So we kept building these different plants up through end plants. And so they all produced all their waste, their product. We're trying to get plutonium out, but you got to send it to these other plants to process it, right? The heavy chemistry that goes into that, and so there's a couple of ways of doing that to get the plutonium out in these places, but the rest of it is all waste. Going to tank farms, encapsulating things, just a tremendous amount of waste to deal with. And so, in fact, we look at the periodic charts, the majority of the periodic charts found in these waste tanks. All the colored items are there. So just interestingly enough, a series of lanthanides. You've got noble gases and a few sporadic other things that aren't found in the waste tanks. But otherwise, it's a chemical alphabet soup that is very difficult to figure out. So we've got a note here, SRS. That's the Savannah River site. That was another site that was built after the war in Aiken, South Carolina, near Augusta, actually, where Augusta National Golf Course is. Just by way of reference. But they did some more production there as well, and they produced a lot of waste. And they're cleaning it up. In fact, since 1983, they've had a cleanup operation going for vitrification, and that's what we're going to talk about in a minute here at Hanford. But they've been doing it for a long time. Well, the Savannah River wastes are what we're saying is a compositional subset. They're just a small subset of the vast array of chemical witch's brew at Hanford. Small and relatively easy cleanup job at Savannah River, even though it's been going since the 80s. There's still a lot of stuff to clean up, but it's a fairly consistent waste stream to deal with. So it's not nearly as complex. So this is to give you an idea of the complexity of the problem, of the reprocessing that was done, of the variety of methods that were done to try to get the plutonium out. It created a lot of waste. And so in the late 80s, then we start to realize, we have a problem here. it's a big problem, and the war's over, what are we gonna do about that? Cameron?
If the waste is all these different elements, wouldn't the waste react with itself?
There's various kinds of reactions, and so we'll look at some of those reactions here.
I'm just still trying to get an idea of what exactly this waste is and why it is
Yeah, I've
waste.
got some pictures of it. So here's an underground storage tank, a cartoon of an underground storage tank, and you saw in the video some of those tank farms that were being built before they got covered up. Okay, so they built them in a big depression, covered them up with soil, so there's some shielding there, right? The thickness of the soil, the distance that you are from it, creates some shielding, because while the plutonium is an alpha emitter, the stuff that's in these tanks is beta and gamma emitters and neutron emitters, and so that's very dangerous to people. So you don't want to be too exposed to those. So in these tanks, there are ways underground. They've got monitoring systems that come up here, but there's again, the composition in here is quite variable, because there's various components. There's a liquid portion at the top, and there's sludges in the bottom, and a lot of salts. A lot of salts become, and again, I'm not the chemist, but the chemistry and the nature of the materials in there precipitate into salts. And the salts tend to get very hard, and difficult to deal with. You can't pump the salts. It's not a slurry so much as just a hardened salt cake. And so, but when they started leaking and realizing that, you get this monitoring equipment, and you can tell that the water level or the fluid level in the tanks after some time is changed, that would be some indication that some of it has gone somewhere. It's left. It's drained out. Not a lot of monitoring put in underground to know where it went. You got to drill holes to see if you can pick up some of that material in the ground. But what they did is they built some more tanks, these double shell tanks, that were built a little bit more with the long-term storage in mind. Okay, so double shell tanks are reinforced concrete in the middle of two shells of carbon steel, and monitoring equipment that goes around both to detect leaks, to understand what's going on. You got the level sensors in there, some monitoring equipment, some cameras in there. The radioactivity works havoc on the cameras as well, so it's a problem sometimes with the cameras getting good pictures of what's inside the tanks. So that's some idea. Layers of sludge, salt cake, some liquids, some solids. It's just a very complex mix of materials in there. And every tank is different, and portions of every tank is different. And so you go down and do a lot of effort, try to get a core in a tank and sample that. That's just what it is right there. It's going to be a little bit different in another spot. So you have to do a really statistically valid mix of sampling in there. Plus, sampling in these tanks, why there's only so many openings here, so you have to build a device that can reach out and get to another spot in the tank, because you can only get down through 2 or 3 holes into the tank. But how are you going to get through this whole 75-foot diameter tank? It's a very, very challenging process. So, we won the Cold War in 1989, and that's when they realized, we need to be about cleanup now. No more production. They stopped all the production, closed the reactors. N-reactor was actually operating through the late 80s, producing both weapons-grade material and power. It was shut down for a normal, you have to go on outages every so often to change out the fuel, do some maintenance, and so in 1987 it was shut down, a normal thing, normal routine maintenance. That was right after Chernobyl. Chernobyl was one of those events where in your life, you remember where you were when certain things happened. And I had just started a job, just graduated from UC Berkeley with my master's in mechanical engineering. I'd gone to work, and so I was at a sort of a facility in Dallas, and we were designing some stuff. And there was a guy there who was a Russian working in the United States there at that company, and we heard about the Chernobyl accident. They had mismanaged their reactor. They have a different reactor design altogether than we do. They had mismanaged that, and it was a huge, huge disaster. It blew up, contaminated the countryside, killed a number of people. It was the worst environmental disaster, at least to that date. I think some people would claim that Fukushima is a bigger disaster today, but don't tell that to the people in Ukraine who live near Chernobyl. It's a ghost town right now. So that happened at that point, and so our leadership decided at that point that we weren't going to start up an reactor again because it was just a political deal. So that was the death knell to N reactor and anything left for production at Hanford. So in 1989, they established the Tri-Party Agreement. The Tri-Party Agreement was between the U.S. EPA, Environmental Protection Agency, the State Department of Ecology, and the U.S. Department of Energy. The Department of Energy is the one who managed the site. They inherited it from the Atomic Energy Administration, sort of morphed into the Department of Energy. So they were the custodian of the problem. The EPA and the State Department of Ecology are the ones who want it cleaned up, saying, hey, there's a big mess here, let's get it cleaned up. So they signed an agreement, 1989, it was estimated that it would take, or at least the agreement said, sort of a contract that said 30 years to clean this place up. 30 years is up next year. They're estimating it's going to take another 50 to 70 years to clean it up. It's so complicated. Okay, so we get into but they've done some things. There's been some cleanup. All the liquids in those single shell tanks have been pumped out into double shell tanks. So there's no more leaking from the single shell tanks. Okay, so that's a good thing. But all the solids are left. What's that?
Does that include the sludges?
No, anything that can be pumped. Okay, and so there's issues with pumping, which is basically liquids. Okay, so anything that's solid, semi-solid, it depends. You can put more liquid in there, but now you're generating more waste. So you have a balance of how much can we liquidize this? How much can we can spray stuff in there to get the salt cake dissolved? But you generate a lot more waste when you do that. So are there ways to chip away and vacuum out the salt cake? And so those are some of the issues that they're working with on trying to clean up these tanks at Hanford. But at least all the stuff that can leak is pumped out of the single shell tank. And finally, vitrification is selected as the cleanup technology of choice. Here, Cameron.
Do the double wall tanks leak at all?
None have leaked to date. But there's monitoring, they're monitoring it, and so they can tell if it leaks, and if it leaks, they'll just pump it out of that tank and into another tank. So the plans are manageable. David?
Has space been considered an option for dumping, just sitting it out of the solar system?
If you, I haven't looked at it, but I know that there's a YouTube video on why don't we send this to the sun. I haven't looked at it. I think that people are very concerned about setting off a rocket with a bunch of radioactive waste on it. Okay? Because if it blows up, right? We're sending rockets are powered by nuclear engines. Okay, so it can be done. I mean, there's risk to settle, but there's a lot of. I mean, the volume here is pretty huge. Okay, and so getting a Tesla into space was pretty challenging, right? How are we going to deal with the billions and billions of gallons here of radioactive waste? So sending it to the sun, it might be on your brainstorming list, but might not be one that you choose right away. So vitrification, and we all know that is making glass, right? Vitrification is to turn something into glass. That's the technology of choice, okay? So let me tell you about how that's going. So at the Hanford site, I worked for, and still do, actually part-time, for the Pacific Northwest National Laboratory. They are one member of the team of companies that work at the Hanford site. They're the longest-standing member at the Hanford site, but the newest member is Bechtel National. Bechtel is a big construction company. Bechtel builds stuff all over the world, buildings and bridges and nuclear power plants, and they're in charge of building the waste treatment plant at Hanford, the VIT plant. And so I'm going to show you a little bit about what's involved with that. I can get the displays to come on. How about there? Okay, let's do that.
For 50 years, just a few miles from the last free-flowing stretch of the Columbia River, the Hanford site produced weapons-grade plutonium that helped end World War II and later the Cold War. This unprecedented effort generated massive amounts of chemical and radioactive waste. 56 million gallons of that waste is currently stored in 177 underground tanks, some of which are presumed to have leaked, threatening the groundwater and the nearby Columbia River. Treating Hanford's waste presents a unique challenge because of its complexity. The Hanford tank waste consists of liquids and salt cake, a material with a consistency like wet beach sand, and deposits as hard as rocks.
So there you can see some pictures that they've taken of what's inside some of the tanks, right? So you've got the liquids out, you can flush some water in to fluidize the material that's in there and pump it out, but as I said, again, that's creating more waste. Cliff?
Why not just leave the solids in there? How does the solid leak?
So as they examine what can be done, what needs to be done, it becomes political. And you'll find this in your career as you get out into industry, that a lot of decisions that are technically sound are not politically viable. And that political and regulations drive a lot of things that you can do, like somebody could legislate, let's send it to the sun, okay? So that would become extremely difficult and expensive. So there's political issues. So leaving it in there, the regulations that have been written say you can only leave so much, and there's too much there. Yes, the do-nothing option is a viable option. Who's going to do something out here in the future? It's not going to be a park, okay? It's not going to be a housing development in Hanford. So how clean is clean? How clean do we have to get it? And even if you try to remove all the materials from the tank, there's still stuff in there, right? One of the options was to vitrify the whole thing in place. And that's the technology that I was working on for many years there. There's a lot of technical difficulties with that we found. A lot of technical difficulties. Cameron?
So again, why is this considered waste? Is it just completely unusable
Right.
at all in
Yeah,
any
it's
form?
not good for much, okay? Some of the strontium that's in there, they're actually taking the strontium out, and they use that to make cancer-fighting seeds. Strontium decays to yttrium, and yttrium can be used in a seed that they can inject into your body right next to the cancer and be a cancer, get the radioactive treatment to your cancer. So there are companies that are doing that. They don't need very much compared to how much is here.
What's vitrification again?
Turning into glass. It's making glass, okay? Like ceramics, only it's a glassy structure. So hopefully we'll talk about that here in a minute. Let me speed this up just a little bit. So you can see what's going on inside this tank.
Waste is the consistency of peanut butter, and each individual tank has its own diverse mix of chemical and radioactive waste.
Tasty.
To solve this problem, the Department of Energy contracted Bechtel National to design and build a facility to treat and immobilize the waste. The Waste Treatment and Immobilization Plant, or VIT plant, will use a process called vitrification to immobilize the waste in solid glass for safe, long-term storage. Vitrification is a proven technology used in the United States and Europe, but never on the scale and complexity of waste found at Hanford. The completed VIT plant will include a pre-treatment facility for separating the tank waste into low-activity and high-level waste streams, 2 vitrification facilities, 1 each for the high-level waste and low-activity waste streams, and an analytical laboratory, and approximately 20 support facilities to provide cooling water, electricity, and other utility requirements. In the low-activity waste facility, waste will be mixed with glass-forming materials and heated to 2100 degrees Fahrenheit in 2 300-ton melters, poured into stainless steel containers, cooled, and prepared for storage. The facility will produce 21 metric tons of immobilized glass per day. In glass form, the waste will be stable and impervious to the environment, allowing its radioactivity to safely decay over thousands of years. The low-activity waste facility is the key component of the department's focus on direct feed low-activity waste, a process which allows for the treatment of low-activity waste in advance of completion of the entire WTP. During DFLAW operations, approximately 1 million gallons of double-shell tank waste will be delivered to the LAW facility for treatment.
So LAW is low-activity waste. It's a portion of the waste that gets separated out into high-activity waste or high-level waste and low-activity waste. That's also more of a political term that I don't want to spend any time on, but there are 2 different types of radioactivity that are going into those places. Jim?
So if it's stable, then why not use the glass for other things?
It's highly radioactive, it's stable. The point is to keep it from leaking. The point is to stabilize it so that it's not going anywhere. So it's
But
not
if
a
it's
danger to
stable,
anybody.
then is it not radioactive?
It's not stable in terms, what they mean by stable is that it's not mobile. It's not mobile in the environment like it is now. Even the stuff in the tanks, who knows? It can still get water in there, it can still leak. So you'd like to stabilize it, and you do it by vitrifying it, because the vitrified products, glass is a very durable waste form. And so when it's subjected to environmental conditions, if they ever get subjected, as it's poured into these canisters or put into some sort of storage, it's not mobile in the environment. So it's not going to hurt anybody by being contaminated. But it is still very highly radioactive. So you have to handle it all remotely. That radioactivity, as we saw, the plutonium and the uranium and other radionuclides in there, some of them are very, very long half-lives, thousands of years. Actually, one of the things, it's been 60 years or so since a lot of stuff was developed. The half-life of strontium and cesium is on the order of 35 years. So maybe we just wait 300 years and it'll all be gone to cesium and strontium. That'll be one thing, but there's still a lot of stuff in there.
What color is the glass? Is it clear?
It's like that one black glassy thing there. So it doesn't. We're not going for color. We're just going for stable and treatment. So it's got so much in there that's black. But if you look at a thin piece of it, it's probably more brown. Okay.
Is it possible to speed up the radioactive process, even if it emits a massive amount of heat? You just go out in the desert and
The radioactive decay process?
yeah,
Unfortunately.
That's interesting.
blow it up with nuclear bombs.
That's mostly set by God.
Exponential.
The decay of radioactivity, yeah. So it's a characteristic of the material. And, but if you can figure out how to speed that up, that would be a good thing.
Tixier. Construction of the low-activity waste facility will be completed in 2018. Vitrification of low-activity waste will begin as soon as 2022. The VIT plant is being designed and built with the highest levels of nuclear quality and safety. All components, systems, and facilities will be rigorously tested during the startup and commissioning phase, before they are declared ready for operations to process Hanford's radioactive tank waste.
So highest levels, nuclear quality and safety. So you don't get much exposure to quality assurance. I think we're talking about trying to put a module of that into IEP2, say, give you some exposure to quality. But you'll get a lot of that in your work. When you're out in industry, there'll be attention to quality in various aspects. Quality and safety tend to be very, very important at places like this. They tend to be, perhaps in the view of some, overemphasized, because at some point when you're trying to be as safe as possible, this is all opinion. This is just my opinion. It's not anything official. You don't get any work done because you're constantly in safety reviews. You're constantly trying to make sure it's as safe as possible, so you can't get any work done. I have a little saying I'll share with you. When safety is job one, no other work gets done. So it's important to have safe and secure operations, but as engineers and scientists, we'd like to think that we can do it safely and still manage our risks. But sometimes the people in charge here, I mean, it's not worth losing one life, right, over doing this. So if you start saying, well, you know, maybe 2 or 3 people might die out of 50,000 that are working here, and that's acceptable. Well, it's not acceptable to 2 or 3 and their families, right? So you need to manage that somehow and make sure that you are working safely but still getting your work done. And the reason that bounces back and forth is because I have to try to do the slides. I have to have the slides go in here while the video ends.
The 3,000 VIT plant employees making this happen are family, friends, and neighbors of those living along the Columbia River. They are proud participants in removing the threat posed by Hanford's radioactive tank waste and protecting.
So family, friends, and neighbors, you're going to get out of college, you're going to graduate, and you're going to move to a community. You're going to have a job. And you're going to be family, friends, and neighbors. Those people there. And the work that goes on in that community, you'll want to be involved in it. So this is, you look at this and it shows up on the news as a terrible hazardous waste site. These are just regular people working here, just regular people trying to do a job, trying to feed their families, trying to have a quality of life. Just happens to be here, happens to be at a place where it's somewhat visible. Wherever you end up, hopefully you consider yourself family, friends, and neighbors of the community that you're involved in, and can be involved in that community, and be a part of what goes on, and take credit for the advancement of your community. So these people are all proud workers there at the Hanford site. Just a couple more things to show you here. We talked about the plant pretreatment. It's very, very challenging. I wanted to show you one more little video here of actual melting. So this is a test that I was involved in. Where we're in our lab is probably about as big as the front of the stage. We've got a melter that's only about this big, and we're simulating that big process, simulating what's going on in these facilities with these big melters. And so what you have here is a little bit of got a pool that's about as big as a coffee can, 10 can is where our melt is going. So this is inside of that circle. There's a couple of plates here. This is joule heating. So you're sending energy to these two plates, these electrodes, to heat up the glass. Look here, that's glass. It's like lava. It looks just like lava, like a volcano. And we've got it contained in a little pool. And then there's a nozzle that comes down here and drips the waste feed. And we're using simulated waste in our process. And that's all the known chemical compositions, but not the radioactivity. Okay. And so we're just turning that into, you can see it bubbling up and cooling and sitting on top of the surface. We'd like to get a lot of it on the surface, because that will help keep the temperature cold in the top, keep it cooler at the top, and help incorporate the stuff in better into the bottom. So it's pretty cool to be involved in some of that research. I just go on and on and on with some of this stuff, so I think I've reached the end of the time. Does anybody have any other questions? Yeah.
I know for a fact that a lot of the elements that are considered part of the waste are extremely combustible, so, or at least volatile.
There was one tank that was generating hydrogen as a natural reaction to the stuff that was in there. Hydrogen bubbles were coming out. It wasn't just leaking a little bit. It was all of a sudden. It was the pressure monitors in the tank. It was all of a sudden there'd be a big pressurization in the tank because the salt cake was covering it. Hydrogen's generating down below. Nobody knows why, and all of a sudden breaks the surface and it explodes a bunch of hydrogen there. I mean, it releases a bunch of hydrogen in there. So now you want to be safe. You want to be careful of what's going to happen for that hydrogen in the tank, because you don't want your tank blowing up. That was a unique event. That's just one example of how the chemical composition in these tanks is so different in each tank, because it wasn't happening in any other tank.
But when you put the waste in there, does it sometimes explode?
No, there's not any combustible nature to all that chemical soup in there. There's not those big concerns.
Is the hydrogen generated through these tanks, like that one specific situation, is that radioactive?
The hydrogen is not radioactive. It's just the whole tank is radioactive.
So you could pump out the hydrogen and literally use it to...
They were able to vent, put a vent in there to release to let it release on a regular basis so it wouldn't pressurize, and then they can use their gas treatment system for that. So it wasn't a big sudden release of hydrogen.
Two questions. So first, earlier you mentioned N reactor and how they produced energy while they were producing material. How exactly did they achieve that?
It was a nuclear reactor. It was like a breeder reactor that both produced energy and produced weapons-grade material.
second question. You said that after the vitrification process, the results are still highly radioactive. So why aren't we using them to heat things like water and produce steam and then use that for energy?
Political. It's another political decision. We could be doing a lot better job with our nuclear fuel cycle and stuff like that, but we don't want to make it look to some of these other countries like we're trying to make more bombs. And so we take a little bit of energy out of them and we leave it. Our nuclear power plants could be doing that too. But now I'm getting into political stuff. So I don't want to do that.
And if you want to get into more political stuff, you can join us for lunch. Thanks, John.
Confused as to why it's considered waste.
Well, it's like a weed.
It's just
A
chemical.
weed is a plant where you don't want it.
Don't log out yet, John.
Okay.
But a weed can't